Okay, so today I'm presenting Nexus, which is a deep learning framework I developed for motor intent decoding. The key innovation is combining EEG and EMG signals, and by fusing these using deep learning, I achieved a 96.5% accuracy in classifying motor intent. The system has significant applications for brain-computer interfaces, especially for patients suffering from neuromuscular disorders. So let's outline some of the key challenges. First, existing brain-computer interface systems use either EEG or EMG signals alone, missing complementary information. Second, signal integration is complex because these signals are recorded at different sampling rates. EEG is recorded at 256 Hertz and EMG is recorded at 1024 Hertz. Third, traditional approaches depend on manual feature engineering, so my solution uses deep learning to automatically learn these patterns. So Nexus consists of 4 stages. Stage 1 is signal processing with modality-specific engineering. Stage 2 is feature engineering, where I extracted handcrafted features and I let a CNN learn these features automatically. Stage 3 is model training with classical machine learning models and deep learning models. And then stage 4 is statistical validation. So this flowchart on the presentation shows how these signals flow through processing, then feature extraction, then model training, then statistical validation. The first stage was computational signal processing. So if you see on the right, these are what raw EMG and EEG signals look like. So the top shows EMG signals with high frequency spiky patterns, and then the bottom is EEG signals, which are smoother brain oscillations. So the data set I used was called the Nebula dataset, which had 8 channels per modality. And then so after pre-processing, I had clean signals. And so the critical achievement for signal processing is called temporal synchronization, which meant that the signals were aligned using neural networks. And stage 2 uses 2 approaches. So for classical machine learning, I extracted 64 handcrafted features. And then from the EEG signals, I extracted sample entropy and power spectral density, or PSD. And then from EMG, I computed mean absolute value, or MAV, zero crossings, and RMS. And so my CNN, the CNN that I created learns patterns directly from the raw signals. And so you can see on the right, this is a feature space visualization using 2 techniques, TSNE, or T-distributed stochastic neighbor embedding, and also principal component analysis. So you can see these are the different classes of motor intent. So you see there's rest, fist, wave, and pinch, and then it confirms it works because these are separated distinctly from one another. So for model training, I compared 4 architectures of the SVM or support vector machines, which achieved an 82% accuracy. Second, the random forest classifier achieved an 85% accuracy. Third, this is a CNN, a one-dimensional CNN, so this is trained on only EEG signals. And then the fourth one was the multimodal fusion CNN. So the multimodal fusion CNN had the best performance, achieving a 96.5% accuracy. And then if you see on the bottom, you have the learning curve. So it shows that the machine learning model plateaus early, while the deep learning model actually continues to improve in its learning. So the bar chart on the right shows that from the classical machine learning model, the best performing was the random forest, to the best performing deep learning model was a 11.5% improvement from 85 to 96.5%. Next is statistical validation. So I used multiple different metrics, and I also performed five-fold cross validation. So the confusion matrices, they showcase important details. The classical ML shows on the left shows that there's some confusion between different gestures such as fist and pinch, while the fusion CNN in the green is nearly perfect with very minimal false positives and false negatives. And the rest specifically gesture achieving 100% accuracy in this first column. And then statistical tests confirm that the p-value or significance value is below 0.001. And then the training plots here shows that the accuracy is increasing while the loss is decreasing. So the advantages over traditional BCI decoding approaches. So why is my system potentially better? First is data driven, so it learns directly from the signals, and it captures nonlinear temporal dynamics. Second is interpretability. So the dual branch architecture lets clinicians analyze specifically how each multimodality, EEG and EMG, contribute individually. Third is extensibility. So the framework has potential to incorporate even more biosignals to determine how well the patient is doing. And then fourth is clinical accessibility. So it doesn't require extensive medical equipment for motor intent decoding. And then show below here are two visuals, and they showcase. The first one shows EEG scalp maps, like where the best placement to for electrode placement to gather these signals, and then on the right is EMG pattern activation maps. And then finally, to conclude, I developed a four-stage framework deemed Nexus, which achieved a 96.5% accuracy. There are two key achievements. So the first is the multimodal fusion and its superiority over a single modality. So it shows that combining signals outperform signal modality approaches by about 8 to 11% in terms of classification accuracy. Next is the end-to-end deep learning pipeline. So it eliminates the need for manual feature engineering, and through the dual branch architecture of the CNN with the late fusion characteristic, it achieved a 96.5% accuracy. So future directions that of my research could include implementation in devices like wearable devices or neuroprosthetics. And then second is the implementation for continuous motion recognition. So this framework addresses significant gaps in the current literature for brain-computer interface systems, and specifically for motor intent decoding.